This is module 3 of FACTS concept related to the shunt controllers. These shunt controllers are compensators. Actually, the objective of shunt compensation and midpoint voltage regulation for line segmentation and end lines of voltage support to prevent voltage instability and improvement of transient stability and power oscillation damping. These are the covered things. Along with in the shunt compensators too, we are we are discussing the thyristor switched reactor and thyristor control reactor and thyristor switched capacitor and a combination of thyristor switched capacitor along with the thyristor control reactors. These are the comes under the shunt compensator second one. So these are under the unit 3 and then we go for the objectives. So the objectives of shunt compensators. So the ultimate objective of applying reactive shunt compensation in a transmission system is to increase the transmittable power. So always the midpoint compensation. So the midpoint compensation always preferred to improve the active power transfer capability. Then go to the shunt connected fixed or mechanically switched reactors are applied to minimize the line over voltages under light load condition and switched capacitors are applied to maintain the voltage level under heavy load condition. That means the shunt compensator always connected nearer to the load to maintaining the voltage stability. These are the direct two achievements after shunt compensation. The active power transfer capabilities increases as well as voltage stability is maintained. Along with you will get the dynamic voltage control. That means you have enhanced the transient stability limit as well as the damp the power oscillations. These two are the another achievements after connecting the shunt compensation. These are the four objectives. First one is active power transfer capability is increased. Second one is voltage stability is increased. Third one is enhancement of transient stability limit. And fourth one is damp the power oscillations. These are the objectives of shunt compensations. We can elaborately discuss each and everything. First we go for the midpoint voltage regulation for line segmentation. Okay. In this you can clearly observe that these are the sending end voltage represented Vs and receiving end voltage represented with Vr. So this is ideal compensator represented as a voltage source. You can see that P is equal to 0. That means the ideal compensator does not involve in the active power transactions. Ideal compensator always influence the reactive power. So for representation it is midpoint. So the total impedance can be divided into two. That is total impedance is nothing but X can be represented by X by 2 and X by 2. The current passes from the sending end to midpoint is represented as ISM and the current is flow from the midpoint to receiving end, that is represented with IMR. So this is simple two machine system with the ideal midpoint reactive power compensator. After connecting this, you can check this phasor diagram. This is corresponding phasor diagram of the two machine system. We know that previously also discussed the sending end voltage and receiving end voltage, Vs and Vr. Previously we are represented as bus voltages E1 and E2 in module 1. So in this Vs and Vr always separated within a load angle delta. So this is representing of load angle delta. So you can clearly represent it in between, clearly midpoint you are representing the voltages Vm. For this particular sake, we can consider all the magnitude. These are some phase differences there, but you can clearly see that we are considering the magnitude is equal. The magnitude, the modulus Vs is equal to the modulus Vr is equal to the modulus Vm, that is equal to V. And coming to this, so this is delta by 2. So after putting the Vm, the entire load angle delta also divided with the delta by 2, delta by 2. ISM and IMR is 2 are the currents. If you increase this, these are VSM voltage, these are VMR voltage. Then you can take any triangle. I have considered this triangle. So that is VS, VSM, and here you see this entire thing is Jx by 2 into ISM. Once you take this triangle means x by 4 again off. You can clearly observe from this. This is Vs, this is VSM. The angle is delta by 4. This is J into x by 4 into ISM. From this you can find out the ISM and VSM. So from this you can take the cos delta by 4 value and sin delta by 4 value. Based on this triangle, you can take cos delta by 4 and sin delta by 4, then find out the VSM and ISM. VSM is nothing but V into cos delta by 4. ISM is equal to 4V by X sin delta by 4. Then you calculate the active power. Active power is nothing but VSM into ISM, that is V cos delta by 4 into 4V by X sin delta by 4. So that's why the entire equal to 4V square by X sin delta by 4 into cos delta by 4. So the active power is equal to 2V square by X sin delta by 4. Like that you calculate the reactive power, you will get the 4V square by X into 1 minus cos delta by 4. So from this we can find out the representing the power versus delta characteristics. After compensating the midpoint, we are representing here that is 2V square by X sin delta by 4. So these are the reactive power representation, 4V square by X 1 minus cos delta. From this figure we clearly understood that the active power capability is doubled after the midpoint compensation. So you can say this is V square by X, this is 2V square by X. From this graph you identify the after midpoint compensation, the active power transfer capability is doubled. So then same, if it is a long transmission line, the requirement of compensators is more. So then we can place with equal distances. For example, you can see this figure. Here we are compensated with three compensators. So all are placed within a equal distance. So that's why you can clearly observe that the reactance of the transmission line is subdivided into x by 4, x by 4, x by 4, like that. So the current also divides like this. This is sending end voltage, this is receiving end voltage. Both are at an angle of delta. In between, we are placing three compensator, three ideal compensator, represented as VA, VM, VN. The three are ideal compensator, which can involve the reactive power compensation. It does not involve the in the active power. So this is the representation. So corresponding, this is phasor diagram. You can clearly observe that, like previous diagram only, we can achieve these things. Okay. So in this, you can clearly see that this is a Vs and Vr are separated within a delta angle. In between, with equal distances, in between we are placing Vm, and in between Vs and Vm we are placing Vi. In between Vm and Vr we are placing Vn. So the currents are represented I, Si, I, Im, and INR and IMN in between them. So accordingly, these are the impedances are divided. It is simply nothing but voltage drops represented J with J, because these are purely inductive in nature. So these are the if some advantage of midpoint compensation to improve the active power transfer capability in the transmission line. Next comes into the second thing. So this is end line voltage support to prevent voltage instability. So that means second objective is our shunt compensation to improve the voltage stability. So that's why you can consider the with compensation and without compensation. You can see that single area system, it consisting of a source voltage is Vs and the receiving voltage is you clearly see that this is a receiving voltage Vr, this is sending voltage Vs, and the transmission line impedance is purely inductive is represented with X. So this is no compensation is there. This is represented as load. Automatically in this voltage versus power characteristics, based on the power factor, the per unit value of the receiving end voltage changes. If it is a lagging voltage, automatically the receiving end voltage value is decreases. If it is a leading voltages, it crosses the rated voltage. So that means the voltage is unstable here without compensation. After connecting the FAC device or shunt compensator are nearer to the load, automatically you can say that previously we can say that the advantage of FAC devices is which is capable to inject capacitive reactive powers or inductive reactive powers. So that's why I'm representing as plus or minus. So otherwise, in other words, you can say that it is capable to inject reactive power or it is capable to absorb the reactive power. That's why we are represented in plus and minus. So these are two different situations are there. If it is considered unity power factor means three situations. Sometimes reactive power absorption is required, sometimes reactive power injection is required. Based on requirement, if it is a lagging power factor, the reactive power, the capacitive reactive power injected into the system to balance the load voltage. So if it is a leading power factors, that is nothing but happened at no load conditions. In this time, it is acts as a reactive power absorber. It can absorb, it acts as like inductive reactor and it can absorb the reactive power to balance the voltage. So after connecting this VAR compensator, automatically the receiving end voltage always maintains some constant value. That's why, so we can achieve that after connecting nearer to the load by FAC device, we can improve the voltage stability of the system. So this is the second objective of the shunt compensators. So these are the third thing we are entering into the third objective to how to enhance the transient stability limit. You can clearly observe from this. So improvement of transient stability. Actually, this is a two-line system. From this equal area criteria is considered for the explaining this transient stability for the two-line power system. From this, you can observe that three conditions: what is pre-fault and post-fault and during fault conditions. You can observe that the fault is here. Before fault, the maximum power will be transferred as per the P equal to E1 E2 by X. Here Vs is Vr, that's why P is equal to Vs into Vr by X into sine delta. If some fault is occurs, no power will be transferred in this line. So only less amount of power transferred in the other line. That's why during fault condition, so the power transfer capability is reduced here. So after clearing the fault, that is a post-fault condition. Sometimes same power, pre-fault power will be transferred. Sometimes some less amount of power transfer. We are considering pre-fault is comparatively low amount of power transfer compared to pre-fault. That's what we are representing here. These are the three conditions. We can analyze that from accelerating area and decelerating area. We can represent the load angle always oscillates in between the accelerating area and decelerating area to achieving the uh, load angle constant. That is a factor. We can clearly explain in this single area concept. We can see the single area system. This is equal area representation of the single area system. This is representing without any compensation. The B figure represents the with compensation. So initially for this analysis, we are considering the always the mechanical power is constant. Always the mechanical power represented is constant. You can clearly observe that this is represented with straight line. So the electrical power is V square by XL sine delta. We are representing with the delta is 0, delta is 90 degrees and delta is 180 degrees. You can clearly observe from that load angle without any fault in the system. The system is operated stably. That means the mechanical power is equal to the electrical power at an angle of delta 1 load angle. The system is operated with stably. In this particular situation, the fault is occurred in the system. Automatically what happened, the electrical power is 0 because this is single line system. So the electrical power is comes to 0. The mechanical power still it is constant. At this point we can achieve that the mechanical power is high compared to the electrical power. Automatically the load angle is varies from delta 1 to delta 2. So after delta 2, delta 1 to delta 2, this area is represented as A1. Here the mechanical power is high and my electrical power is 0. That's why this area is called as accelerating area. So in this delta 2, if the fault clears, what happened, you can clearly see that this is mechanical power. If the fault clear, electrical power can be appeared here. So in this situation, the electrical power is high compared to mechanical power. Automatically what happened, uh, again the load angle changes from delta 2 to delta 3. So that's why here the mechanical power is low compared to electrical power. That's why it is called as decelerating area, represented as A2. So the load angle always oscillates in between the area 1 and 2 to reduce the oscillations. So these are the margin available for area 2. Automatically, if the system crosses this margin, automatically the system is failed, collapse. So the particular angle, limit angle, the final angle is delta critical. If the load angle crosses the delta critical value, the system is under trouble, that is collapses. So after putting the midpoint compensation, the power is increased. You see like this. This is 2V square by x sine delta. Same concept here. The accelerating area represented as AP1 and the decelerating area is represented as AP2. The margin which is here available is AP margin. So from seeing this, compared to A margin, AP margin having higher area. And delta compared to delta critical value, here the delta P critical value is equal to 180 degrees. That means the system here, for example, it crosses the delta critical value, almost it comes 160, 170, the system will be collapsed. But here it comes up to 180, the system will be stable. Once it crosses 180 only, system will be collapsed. By seeing this also, this having maximum area is there to settle this transient issue. That's why we can see from these two analysis, these two figures, we can clearly say that uh, after applying the midpoint compensation along with the active power transfer capability, the transient stability limit is enhanced. So this is related to the enhancement of transient stability. Coming to the last one, fourth objective is power oscillation damping. So you can clearly see that undamped and damped systems. So previously we discussed that the load angle is changes from delta 1 to delta 2 and that is accelerating, and next it is changes from delta 2 to delta 3. So once it converts, it comes to accelerating means positive, decelerating means negative. That means the change is always plus d delta by dt and minus d delta by dt. Like that, the load angle is oscillates. That is represented as undamped system. Once the load angle is changes, power is always depends upon the load angle. We can say that delta is a P is equal to v square by x sine delta. Once delta oscillates means automatically power oscillates. That can be reflected here. So our aim is to compensate. Our aim is to damp the power oscillations. That can be, you can see always the advantage of fact controllers is capable to generate, are capable to absorb, are capable to generate the inductive reactive power or capacitive reactive. If you consider one is positive, another thing is negative. Like that, you give the both the commutations. Comparatively, the system is comes into the delta values comes into the damped. Damped means it comes to nearly delta naught. If delta is settles, load angle is settles automatically, the power is also settles. Then you can reduce the compensating magnitude also. It comes to zero next cycle. So that's why fact devices is indirectly help the uh, help to reduce the power oscillations. That is nothing but damping the power oscillations. So these two are the advantages in this. These are the four objectives in the particular thing. And we can discuss some different types of fact controllers. That is, you can clearly see that these are the different types of fact controllers or shunt compensators too. That is thyristor switched capacitors and thyristor switched capacitors and thyristor controlled reactor combination. In this also previous slides we can discuss the thyristor switched capacitors and thyristor controlled reactors and switched reactors also. Along with we will discuss about some SVC STATCOM issues and the regulation and slope of the slope and transfer function, dynamic performance, and again comes into the how it is enhance the transient stability and how it is damps the power oscillations, like that operating point control and overall summary of the compensating control or comes into the shunt compensators. You see first elaborately, these are the thyristor controlled and thyristor switched reactors. You can clearly see that the arrangement is, it consists of two anti-parallel thyristors connected to the inductor. So this is purely inductive. That's why the waveform representation is you see. This is a voltage. You can say that this is shunt connected device. Only influence on the current. There is no change in the voltage. That's why inductive, this is inductive circuit. That's why purely 90 degrees lag the current, that is IL. The firing angle is 0. Then alpha value increases. Alpha means firing angle. If you increase the alpha value, automatically the magnitude also reduces. Same waveform is represented in negative circuit. Here, negative representation of voltage. After 90 degrees lagging, current is started. If alpha increases, magnitude is reduces because IL of t is simply V by omega L into sine omega t minus sine alpha. If the alpha value is 0, IL is maximum. If alpha value is increases up to 90 degrees, the magnitude also reduces. Like that, we are controlling the current which is injected to the transmission line. Because this entire system is connected parallel with the transmission line, we can control that. In this same operation for thyristor control reactor, switching reactor, and control reactor having advantage compared to switched reactor. Switched reactor having limited capabilities. Stepwise we can control like 1, 2, 3, 4. If it is a controlled reactor, we can control from initial to maximum at any compensation. But cost point of view, thyristor controlled reactors are cost compared to the thyristor switched reactors. So you can see with the different firing angles, you can clearly understood the basic operation of thyristor controlled reactor. Alpha equal to 0, that means the magnitude you can observe. The voltage magnitude is not changes, this is entirely constant. We can say that shunt factorizes always influence on the current. So alpha equal to 0, it is a maximum current. If the alpha 1 is more than 0, that's why magnitude reduces. Alpha 2 is more than alpha 1, that's why again magnitude increases. Like that, if increasing the alpha value, the magnitude of current will be decreases. From this diagram, we can clearly understood the basic operation of thyristor switched reactor and thyristor controlled reactor. These are the BI characteristics of TCR and TSR. Then you come to the thyristor switched capacitor. Thyristor switched capacitor, you can clearly see that anti-parallel thyristors are connected in series with the capacitor. Such a large inductor is there to avoid the some sudden changes for safety purpose, simply protection. Same operation, but you can, this is a capacitive circuit, that's why current is in leading condition, voltage at lagging condition. This is also shunt connected circuit, that's why the voltage is always constant and current is a magnitude changes. And you can clearly observe that here two conditions, thyristor switched capacitor is on condition and off condition. If the on condition, current passes. If it is off, current value is 0. The voltage across the switch, if it is working means short circuit, it comes 0. If it is not working means you will get the V voltage appear across the switch, that is VST. So this is basic fundamental operation. Based on the designing of the capacitor, thyristor controlled capacitor is not, operation is not possible. And this can be achieved in the with some combination. So these are the some fundamental equation of thyristor switched capacitors. We can consider V is equal to V sin omega t. Then current is equal to I of omega t is equal to V into n square by n square minus 1 WC cos omega t. N always represented as square root of Xc by XL. So then the capacitor voltage is equal to n square by n square minus 1 into voltage. So this is the thyristor switched capacitors. Due to constructional point of view, thyristor controlled capacitor operation is not possible. That's why that can be achieved by using this combination. This is also called as SVC, static wire compensator. The arrangement of thyristor switched capacitor along with the thyristor controlled reactor. In this figure you can clearly see that here some of the things, 3 thyristor switched capacitors are connected in parallel along with the thyristor controlled reactor. From this combined operation, we will achieve both inductive reactive power and capacitive reactive power. You can clearly see that this is representing QL demand and this is QC demand. That is QC indicating the capacitive reactive power. This is QL indicating the inductive reactive power. From this operation, you clearly see that the 3 capacitors is not operated. Only inductive power will be injected in the transmission system. That is represented from here 0 to this value. This is purely inductive. Once the inductive reactive power and capacitive reactive powers all are not operated, it comes to 0. Then if you switch on this SW1, that means the capacitor is at on condition. The capacitor is injecting capacitive reactive currents, capacitive power, capacity to react to power into the system, you will achieve this much power. If it is connected to, you will achieve this. If the three capacitors are connected, you will achieve this power. So entire smooth operation is possible from this point to this point. This is represented as QL value. For variable capacitance operation point of view, we are varying sometime maximum to minimum and minimum to maximum, maximum to minimum and minimum to maximum. Like that, we will achieve this entire characteristics. So this is the thyristor switched capacitor and thyristor controlled reactor operation. So coming to the next is static wear compensators, SVC and STATCOM. So the basic difference between the SVC and STATCOM is that. So this is SVC always a combination of variable impedance and variable impedance type. That is, maybe it is a capacitive in nature or inductive in nature. This is a static wear compensator. STATCOM always depends upon converter based. Maybe the first block for the STATCOM is voltage source converter. We are discussing in the module 2. Like that, these are the converter based or variable impedance type fact devices, whether it is SVC or STATCOM. Here we are representing the general control scheme for static wear generators. You can clearly observe that here uh, this is representing a generating station along with the transmission line, representing here some generating station. These are the impedance of the transmission line, and this is representing the terminal voltage VT. This can be measured here. This can be compared with the reference voltage. The error can be generated, that is delta VT, that can be injected into PI controller to converting equivalent current. Some direct inputs also added. So the IQ reference is generated based on this error voltage. This is input to the static wear generator. Based on the IQ reference value, the static wear generator inject the capacitive currents or inductive currents to minimize the delta VT. The perfect regulator operation is always delta VT is equal to 0. That means terminal voltage is equal to the reference voltage. Like that, the static wear generator is operates. So this is the basic concept of the different types of compensators like SVC, STATCOM. Coming to the regulations load, these are some VI characteristics of SVC and STATCOM. Here we can clearly observe that we are considering three load lines. One is equal to the terminal voltage, one is above the terminal voltage, one is below the terminal voltage. So three types of load lines are considered here. So SVC is gradually increasing and STATCOM is in spot increasing. This is based on the converter based and this is based on the variable impedance type. So here the left hand side is related to the capacitive currents and right hand side is related to the inductive currents. You can clearly say that here the terminal voltage is equal to the referent voltage, so there is no need of any compensation. That's why 0. You can see here load line 3, load line 2, you see load line 2, it touches the VI characteristics at this point. That means load line 2 is always representing the below the terminal voltage. That's why the capacitive currents is required to compensate. You can see that clearly IC2 current is required to inject in the transmission line to compensate these low voltages. Automatically the voltage capability is increases here. The voltage is increases here. Like that, you see this is above reference voltage, above terminal voltage. So you can see that this can touch this point. So this value is a more than the actual voltage, that means rated voltage. So then you can inject inductive currents, that is IL3. So before compensation, the difference is like that. After compensation, it is reduced. Like that, this SVC and STATCOM can be operated. Same thing you discussed in the previous objectives. By using this, you will get the transient stability enhancement as well as the power oscillating dam. So these are the key factors after connecting the compensator in parallel. So interface between the high power and high voltage semiconductor valves of the overall switch converter or TSC and TCR structure, and a highly sophisticated real-time control required for the internal operation of the VAR generator and for the desired system compensation functions, signal measuring and processing circuit for the system, and equipment variables. So these are the shunt compensators. So this I will finish this module.